Coefficient of determination, often expressed as r squared. Coefficient of determination is the proportion of the variation in y that's explained by the regression. So before we proceed with the analysis, let's see if we want a high coefficient or low coefficient. Well, if the coefficient of determination is telling us the percentage that's explained by the regression, that sounds like a good thing. So the higher the coefficient of determination, the more explanatory power the model has, and therefore the better it is for forecasting. So with that big picture developed, let's go have a look and see how we can calculate coefficient of determination. There's two ways to do it. In the first approach, what we do is we take the total variation in y, which is the dependent variable, and then we break it down into the component of that total variation that's explained by the regression, and whatever's not explained by the regression will be explained by the errors. So you only have two buckets to explain what's happening to the dependent variable, the regression and the error. Now the question is, how do we quantify the variation that's captured by the regression and the error? So first of all, let's look and see how total variation itself is quantified. We do that by taking the total sum of squares. And we're going to see the computation of these sums of squares when we get to the ANOVA table in a subsequent module. But basically for now, what we need to know is that we are quantifying the total variation in y and trying to see how it's allocated between the regression and the errors. Now the portion of variation captured by the regression is represented by what's called the regression sum of squares, so RSS. So that's part of the total variation that's captured by the regression. And then again, the part that's not explained by the regression is caught by the errors. And to quantify the variation captured by the errors, we look at the sum of squares of the errors, or SSE. So therefore, once we've quantified all this variation, we can calculate our squared as follows. And this here is just straight out of the narrative that we looked at over here. R squared is the percentage of variation, or we should say percentage of total variation that's explained by the regression. And you can see that right here. Here's the total variation, which is quantified by total sum of squares. But we want to know what portion of that is captured by the regression. And that's quantified by the regression sum of squares. Now the other way we can express the regression sum of squares is as follows. We know that the total is explained either by the regression or the sum of squares or the errors. So therefore, it's a straightforward algebraic equation. So to solve for RSS, we look and see what's left from the total after removing the part that's explained by the error. So that's the other way this framework may be rewritten. Now the second approach to calculating coefficient of determination is by simply looking at the square of the correlation between x and y. And that's it. So for example, if the coefficient of determination is 0.62, so we're talking about this guy right there, that would imply that the regression explains 62% of the variation in y. And as I said before, the higher the coefficient of determination, the more reliable the model would be.